Hi. Let's see how to do this kind of question. A space capsule here. Let's say this is a space capsule. Now it's entering the atmosphere. Okay, let's say this is the Earth. This space capsule is quite a distance away from the Earth. Now, what about the speed they said initially? The speed they said traveling at initially 35 meters per second. Okay, this one is traveling at 35 meters per second. Okay, what are the forces acting on this space capsule initially? Definitely, it will be the weight and the frictional force R. They give you the frictional force R is equals to kV squared. Okay, now what is the first question that they ask? They ask you what is the resultant, the initial deceleration, they ask. Okay, let's solve question A here. Now, what is the initial deceleration? We use Newton's second law F net equals to ma. So what is the F net? F net will be R minus W or W minus R. It doesn't matter. So let's say we use R minus W equals to ma. So R is what? R is kV squared, as stated here in this section, minus the W is mg equals to ma. Now, what is the A then? So it's A is equal to kV squared minus mg divided by m. K is given at 5, so 5, speed is 35 square minus m is 260. Okay, 260. G is 9.81 because they said it's falling at 9.81. Actually, this is not true because from here to here there's still certain distance. 9.81 is only true on the surface of the Earth. From here to here, the G is actually increasing. Here is actually lower, maybe only 8 or 7. Okay, at this instant. But they say assume to be constant 9.81. So we just use a number. So divided by the mass is 260. So let's take out a calculator and count what is the value of acceleration. Now we will get A is equals to 13.7 meter per second squared. Okay, let's deal with part B. Part B, they ask you about terminal velocity. Well, what do you understand by terminal velocity? Do you still remember? When terminal velocity, all the outward force must be equals to downward force, right? Because at this instant there will be no acceleration. This is the meaning of terminal velocity, in which the object has reached maximum velocity. So in this case, at terminal velocity, resultant force is 0. What is that? What does that mean, 0? 0 means R equals to W. R equals to W. Okay, so R is kV squared. W is mg. So in this case, the V will be equals to mg over k square root. So just plug the value inside. You will get square root 260 times 9.81 divided by the k value is 5. Okay. So what is the value of the speed? The value will be 22.6 meters per second. Okay. Now, let's proceed to do section C. Okay, let's scroll down a bit. Okay, how do we get the rate at which the capsule is doing work against air resistance? Okay, in this case, we need to get okay, we need to revise back a little bit on the formulas about work energy power. First of all, we need to understand about this formula. This is all the while the formula that I've taught you about conservation of energy. Change of E. Okay, big F minus small f times D is the net work done, equals to change of KE plus change of GP plus change of EPE. Okay, this is the COE equation, conservation of energy. But in this case, they ask you about rate at which work is done against friction. against air resistance. Okay, the rate at which work is done against air resistance means what? A rate means divided by the time. So when everything divided by the time, this equation becomes power. Okay, now but it doesn't matter actually, we just divide by time. Now, so in this case, what they want work done against friction, rate of work done against friction. Which terms here represents rate of work done against friction? Okay, let's see term by term. Okay, this F obviously not exists because there is no continuous external force that pulling the spaceship downwards. Now, what about this F times Z over T? Yes, this is the one. This is the rate. This is the work done against friction. This is the whole thing is called rate of work done against friction. So in other words, your job is to find FD over T. So this is the answer. But is that the only way to do it? Okay, we do not know. Okay, let's continue. Delta K over T. Any changes of kinetic energy? They say when it is traveling at terminal velocity. Terminal velocity means speed is constant. So there is no change of Ke as well. Obviously here it has no spring, so you do not need to care about the spring energy as well. So this one will be delta GPE over T. So in other words, your answer will be equal to either this or this. The negative just means is that the energy is lost. So we just care about the magnitude, it doesn't matter, okay? Let's try to find part C. So F is what? F is the friction. The friction is what? The friction is R actually. R is the friction, okay? So R is equals to kV squared. So this one must be F alone is kV squared. D over T, what about D over T? D over T also speed. The distance divided by the time is speed. So kV squared times V is kV cube. Okay. And now let's say we try to solve using kV cube. K is 5. V is at terminal velocity. V is, we found it just now, is 22.6. Okay, let's see what is the final answer for that. Let's take out your calculator and count. .77 times 10 power 4. Okay, let's say if you are not convinced that this is the answer, okay, we can also use this to solve the problem. Let's see what is the change of KE. What is the change of GPE? Okay, change of GPE is mgh over T. Okay, but h over T is distance over time. It means speed as well. In other words, you are looking for mgv. What is mgv? M is 260. G is 9.81. V is 22.6. You will get about 5.76 times 10 power 4 watt. So they are very close to each other. Okay. Now how about section D here? Okay, look at section B. Explain whether the value obtained in C is an overestimate or underestimate. Okay, look at this question. Now, this is the answer for section C here. Look at this equation. The answer for C is mgv. Anything wrong with this value here? M, anything wrong? Anything wrong? Wrong assumption about M? Basically no, because M is constant. What about the speed? Any wrong assumption about the speed? Also no, because the speed we already reached terminal velocity, so V is still at 22.6. But G is the problem. Do you realize that G actually changing all the time? Just now I've mentioned to you that for this place, the G is actually keep on increasing from here to here. Okay, but actually in this place, the G is lesser than 9.81. So in this case, the value you get for this one is actually larger than the value when the object is actually still in the mid-air before it reaches the Earth. Alright, so in other words, this value is an overestimate. It's an overestimate. Because the G here, because G at space is lower than 9.81 meter per second square. That is the answer.